Hey guys, welcome back. Welcome to second semester. Hope you guys are doing well. Okay, so today's lesson is going to be completely new, not very difficult. Let's start by reviewing something from your past. Okay, so way back, like the first week of school, we learned how to estimate a derivative using a table. And I think it should make sense that since derivative means slope, then when we estimate a derivative using a table, we basically calculate the slope surrounding the value in question. So I would use these 2 points. So my estimated derivative would be subtract the y's, subtract the x's. Okay, Algebra 1 slope formula using the two values surrounding the point in question. So this would be 3 over 2. So that's just a review of what we did way earlier in the year, estimating a derivative. Okay, it's the Algebra 1 slope of the secant using the 2 points surrounding the one in question. Well, today's question is going to be, how do we estimate an antiderivative? So this is our goal today. So maybe, hopefully you remember that an integral is actually the area under the curve. So let's first find an exact answer and then look at all the different ways that we can estimate. So if I wanted to know the actual area under this curve from 0 to 4, so I'm talking about all of this area perfectly shaded in. If I wanted to know what that area was, stopping here, going from 0 to 4, then it would be the integral from 0 to 4 of that curve, which is x squared plus 1. Okay, that's the exact area under the curve. And we know how to do that integral, so we can find the exact area under the curve. We do the antiderivative, then plug in 4 and plug in 0 and subtract. Oops, this is a little out of order. Okay, so that's the exact area under the curve. And that would be the entire shaded region under the curve from the curve to the x-axis. Alrighty, so that's the exact answer. But sometimes you don't have the equation and instead you have a bunch of values. So how do we estimate the area? Well, instead of finding the total area, we can make little rectangles that approximate the area under the curve. So the first one we're going to do is a left-hand approximation. We call it a left Riemann sum. That was the title of the slide that we started with, a Riemann sum. Okay, a left Riemann sum would look like this. Okay, now obviously that area isn't perfect. It doesn't completely fill the area under the curve, but it's an estimate. And if we used more rectangles instead of just 4, if we used a whole bunch of rectangles, like 40, then the area would get even closer to being accurate. Okay, but now I'm just going to show you the mechanics of doing a left Riemann sum. So it would be the area of these rectangles. So the approximate area for a left Riemann sum, sorry I messed that up, would be adding up all of these areas. 1 times 1, 1 times whatever this height is. Well, that height is what you get when you plug the 1 in right here. So it'd be 1 times 2. That's a height of 2. Doing the area of each rectangle. The next rectangle would be 1 times the height here. Well, the height at 2, we'd plug in the 2 right here, we'd get 5. And then the last rectangle would have an area of 1 times whatever the height is right here. Okay, well, plugging in a 3, that height would be 10. Okay, now a couple of tidbits. First of all, they all had a width of 1, so we could have just written it once. But even if it's a 1 on the AP exam, this is usually a free response question, and you have to write the 1, even though we all know multiplying by 1 doesn't do anything. Totally stupid, but you won't get credit without it. So notice it's the width of the rectangle times the height each time. Okay? Well, what is the height? It's the height at the left side of the rectangle when you're doing a left Riemann sum. And notice we did not end up plugging in this 4. Okay, so for a left Riemann sum, you end up plugging all the left points in. All right, now what is that actual answer? Let's see. 1 plus 2 plus 5 plus 10, so total area of 18. And remember, that was below the actual area, and you can see why. Look at all the missing space. Okay, left Riemann sum. Now let's do a right Riemann sum. Okay, this time the height of the rectangles starts on the right end point and goes over. Okay, so we start here and go over. Start here, go over. Okay, and you can see that that is an overestimate of the actual area under the curve. And again, if we'd used thinner rectangles and used more of them, we would get an even better estimate. So now, calculating a right Riemann sum, I'm going to start on the right side and find the area of each rectangle. So it's a width of 1 and a height of whatever you get when you plug in the 4. So when we plug in a 4 here, we'd get 17. Then we're going to do the next rectangle. It also still has a width of 1 and a height of whatever you get when you plug in 3, which is 10. Next rectangle is 1 times whatever the height is here when you plug in a 2, which is 5. And the last one is a width of 1 and a height, whatever you get when you plug in 1, which is 2. Okay, now notice for a right Riemann sum, you don't end up using this point. We didn't use the height at 0, we used the height at 1. So for a right Riemann sum, use the height at 4 and over, then we use the height at 3 over, height at 2 over, and the height at 1 over. We didn't end up using a height of 0. And you'll see why this is helpful in a minute when I just give you a table. So again, you can see this one is an overestimate of the actual area. And we'll talk more about why it's an overestimate or an underestimate probably tomorrow. All right, so now let's talk about how you'll do these things when you're giving a table. Here we want to estimate the area from 0 to 8. We're estimating an integral. Remember, to estimate a derivative, you use slope. To estimate an integral, you use area of rectangles. And they'll tell you whether they want you to do a left or a right Riemann sum. Well, this time we're going to do a left Riemann sum. Now, I could graph this, or you'll see a shortcut in a little while. So since I'm doing the left Riemann sum, let's put the x's. We're going to have a 0, 3, 4, 5, and 8. And the height of my rectangles is going to be starting on the left side. So at 0, we go up to 3 and over. So that has a height of 3. Then at 3, I'm going to go up to 2 and over. And you don't even have to worry about drawing it to scale. At 4, we're going up to 3 and over. And at 5, we're going up to 5 and over. It's a left Riemann sum, so I used all of these numbers except for the last one. Notice the 6 didn't show up. So if we calculate the area, the first rectangle will be 3 times 3. So the integral from 0 to 8 is approximately, 3 times 3 for that one. The next one is 1 by 2. The next one is 1 by 3. And the last one is 3 by 5. Now, again, you do have to write all of these numbers on the AP exam, okay? Now, we'll get the answer in a minute, but now look at the table and see how you could avoid doing all of this work making this picture. It's really a waste of time. If you look at the table, we could have figured this out just by looking at the table. The width here, the width here is a difference in the x's. So it's 3 minus 0 is 3, and then you use the number on the left for a left Riemann sum. For the next one, this guy, it's 4 minus 3 gives me that 1, and I use the number on the left, 2, to get this guy. For this one, it's 5 minus 4 gives me that 1, and using the number on the left, the 3. And last, 8 minus 5 is 3, use the number on the left, 5, and you don't use the right number when it's a left Riemann sum. Okay, maybe pause and rewatch that video so you can see how to do it quicker without having to draw the graph. Okay, just to get an answer for this, we would add all that up. So let's see, it is 29. Final answer. All right, let's do a right Riemann sum approximation. Okay, new problem. So I'm going to do it the shortcut way this time. So a right Riemann sum means we start on the right side, and the integral would be approximately the width of the rectangle, the width of the rectangle is 3, and the height would be the number on the right because I'm doing a right Riemann sum. By the way, get rid of those directions. This is going to be a right. Okay, my next rectangle would be 7 minus 6, which is 1, times the number on the right, 3. The next rectangle would be width of 1, height using the number on the right. And last, 5 minus 0, which is 5, number on the right, 5. Because we used a right Riemann sum, the 7 didn't get used. Okay, then you just do the math and add it up. But make sure you always remember, for a Riemann sum, it's always a free response question, and you have to write all the numbers, even when there's a stupid little one. All right, add that up, we get 6 plus 3 plus 4 plus 25, which is going to be 38. All right, let's have you try one. This is a right Riemann sum. Hit pause and see if you can do it on your own. Okay, hopefully you did it the quick method. It would be 3 times 6 plus 1 times 5 plus 1 times 3 plus 3 times 2. Okay, I started graphing it just to show you why it is those numbers if you didn't get the shortcut method. Let me erase this. Okay, the graph would be at 8, I have a height of 6. So we go to 8, up 6 and over. At 5, I have a height of 5, over. At 4, I have a height of 3. And at 3, I have a height of 2. You end up not using the 0. Okay? So the area of these rectangles matches these numbers. Final answer, multiplied out, added up, 18 plus 5 plus 3 plus 6. And what do you get? 32, I think. So that's a left and a right Riemann sum. And go figure, we also have a midpoint rule. They don't call it Riemann sum anymore. It must have been someone else who figured it out. So now it's a midpoint rule, but it's the same idea. They will tell you how many subdivisions to use for a midpoint rule. Okay, so I always, for the midpoint rule, I still have to graph it because I'm visual on these. So I'll show you how to graph these. That says 2 subdivisions. That means 2 rectangles going from 1 to 5. So I'm going to first figure out what to count by. So 1, 2, 3, 4, 5. And I need to cut from 1 to 5. I need to cut that into 2 rectangles of equal width. And I just draw them random heights. So I'm going to say, oh, it'd have to be cut up kind of like this. Same width. Then the height of those rectangles, since this is a midpoint rule, the height is determined by the number in the middle. Go figure. So this first rectangle would have a height, whatever the height is, at 2, so it's a height of 4. The next rectangle would be the height at 4, which is 6. Now find the area. It's 2 times 4 and 2 times 6. That's a midpoint rule. So 8 plus 12, 20 is my answer. Okay, so you could do this one without having to graph it, but I usually have to graph it. I'm just visual on the midpoint rules. All right, next what we're going to talk about is what do you do if they don't give you the table, okay? So remember, area under the curve is actually the integral, but we don't want to integrate and do a Riemann sum. A lot of people accidentally do that. Don't integrate. A Riemann sum is an estimated integral. So don't do an integral and then do a Riemann sum, okay? So for this, what you could do is make your own table. So I'm going to do it the long way. I could say, okay, I need 4 subintervals going from 1 to 9, and I could plug in 1, 2, 3, all the way up to 9. But that is a waste of time because I don't actually use all of these numbers. I could do it like this. Plugging in the 1, we'd get 2. Plugging in a 2, I'd get 5. Plugging in a 3, I could do that. But since I know I'm going to do a midpoint rule and I'm only going to use the numbers in the middle, it's actually easier to just find the ones you actually need. So here's what I mean. I have to go from 1 to 9. I'm still going to do from 1 to 9. I'm going to go ahead and count that out. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to make 4 rectangles. Well, we're going from 9 to 1. That would be 8. Divide by 4. I'm guessing that they need to be width of 2. Let's see if I'm right. Yeah, that works. And yes, you can always do that. All right, now the height of those rectangles is going to be what you get plugging into this, each of those numbers in the middle. Plugging in a 2, I'd get 5. Plugging in a 4, 17. Plugging in the 6, 37. And plugging in the 8, 8 times 8, 64, 65. And now I can easily get the integral that approximates the area is the integral from 1 to 9. And it is approximately width of 2 for all of these. So 2 times 5, 2 times 17, 2 times 37, and 2 times 65. You can add all that up to get the final answer. Okay, that's a midpoint rule. When they don't give you the table, you can either make your own table or just do a quick approximation. Obviously, this is not drawn to scale. I put the 37 below the 17. I don't really care. This is just for my own visualization. All right, so that's pretty much it. I have a worksheet for you to practice. Hope you're doing well. Be sure to message me if you have any questions. Good luck. Bye.